Yes, but perhaps we can begin now. So, welcome everybody to this week's Majorana-Raychaudhuri seminar. Today we have Abhishek Kumar Mehta as our first speaker, and he's going to talk about non-thermodynamic black hole evaporation. So, maybe I will send you a reminder when 5 minutes are left.
Sure. Cool. Oh, so I should start now, right?
Yes,
Yeah.
we are
Okay.
live on YouTube as well.
Okay. Okay. Hi, everybody. I would like to thank the organizers for extending this invitation to me so that I can speak about my recent research work. So my name is Abhishek Kumar Mehta, and I have been pursuing this research topic with my collaborator and friend, Professor Ivan Araut, who is currently positioned in University of Saint Joseph in Macau. And the reason we started looking into this problem, um, just a minute, let me see if I can. Yeah. So the reason we started looking into this question is because when we study black hole evaporation, for instance, you come across this consensus that the only way black hole evaporation can take place is through thermodynamical means. And we started thinking, what are the principles, or what is it about the whole process that forbids uh, other modes of black hole information? Why is it that black hole evaporation? Why is it that black hole evaporation only occurs through thermodynamic means? And the reason why this is a little it's a little unclear is because if we couple quantum fields to a metric background, especially a metric that has a changing mass parameter such as the one that I have used here, um, the field equations, the semi-classical field equations will give you the rate of change of this mass parameter in terms of in terms of the expectation value of the stress energy tensor, of the coupled fields. Now, if you look at equation 3, you know, uh, it's not immediately clear whether equation 3 will immediately give rise to an evaporation configuration or an accretion configuration. Accretion would be like the opposite, like the black hole simply is, consuming matter and becoming larger and larger, as opposed to evaporation. So, when you are coupling quantum fields to such a metric, it's not very clear from the computation itself that you would only have evaporation processes. So that is one aspect, and second aspect is that even within the evaporation configurations, it's not clear that all configurations would be mediated by thermodynamical processes. Okay. And if you were to take the claim that all black hole evaporation has to be thermodynamical, what you are essentially saying is that if the time derivative of the mass parameter is negative, you should see the same profile for a large class of theories. Where for not large as in those class of theories where you have the time derivative negative. So it should have the same profile, and this does not seem very obvious from the way equation 3 is written, or rather formula 3 has been derived. So, and if you wish to verify this claim that thermodynamically mediated evaporation is the only means of evaporation, you have to verify this for individual theories, right? And that does not seem very practical. So, one can ask, how may I even test such a claim? And that can be done if you make an observation here that this sort of looks like a formula for a field M itself. So if you can somehow have an effective field theory for the mass parameter itself, we can probably derive its equations of motion. And if the solutions to the equation of motion always look like this, then you can say yes, thermodynamically mediated evaporation is the only means of black hole evaporation, right? So that is what we decided to test. Actually, this is what our research uh, direction was. So how can I derive such an effective field theory, an effective field theory for the mass parameter? So before I continue, I would like to know if I am still audible to everyone. Um,
Yes, yes.
yeah. Okay. Cool. So how would I derive the effective action for the mass parameter? So I would simply what I would simply do is integrate out the field I'm coupling to the metric. Actually, for simplicity, I would be working with the Vaidya metric because it's a lot easier to work with. So what I would do is I would couple a scalar field to minimally to the Vaidya metric, a massive scalar field. I mean, I'm considering a massive scalar field for simplicity now. You can consider any general theory, and I will simply integrate out the scalar field. And what I would be left with is an effective action in the mass parameter. And I would find the equations of motion of this mass parameter and try to solve it and see what kind of profiles, what kind of mass rates I can derive from that. So, so if you do that by implementing the right boundary conditions, you would get some effective action of this kind. Yeah, the calculations are a little tedious, but they are straightforward. So I'm not going to go into that detail, but you can derive an effective action for the mass parameter, and this is the equation of motion for the case where we are discussing massive scalars. And if you try to solve it, one of the solutions uh, look like this. And this solution is very interesting because the time derivative is actually positive here. So this is not an evaporating solution. This is actually an accreting solution. So from here, what we learn is that just because you couple quantum fields to a background scalar, a background metric, an evaporating solution is not guaranteed. So this actually justifies our suspicion that maybe thermodynamical means uh, is not the only means of black hole evaporation. Okay. And this solution which we have obtained is actually very familiar, will become more familiar if you go to large mass regimes. In the large mass regimes, the rate of um, change of the mass parameter is proportional to m square, and this is the same profile you also see in the Bondi accretion formula. So this is the Bondi accretion formula, and as you can see that there is a consistency here. So from this whole methodology, you can actually get a very sensible answer. You know, so it also kind of justifies. So it's also like a consistency check, you can say, of our computations. You know, and now and from here we can actually get a very simple evaporation profile. And to do that, I will allow m square to take negative values. If you allow m square, it's just a test, right? So if you just allow m square to take negative values, maybe the time derivative of the mass parameter will become negative, and it will become an evaporation profile. And when you do that, you kind of get your first non-thermodynamic evaporation, actually. And the interesting thing about this um, evaporation configuration, this evaporation profile, is that it has a remnant. As in, if the mass of your black hole, if the initial mass of your black hole is greater than some cutoff mass, it will decay to that cutoff mass. And if the initial mass of your black hole is smaller than a cutoff mass, it will cascade, as in it will accrete to become larger, and again go back to this cutoff mass. And this is essentially the behavior of a remnant. So what we have essentially derived is a evaporating black hole solution that that has a remnant. Okay, and this is simply from the solutions to the equations of motion of the effective action for the mass parameters, right? And you can also we worked with massive scalar fields, but you can work with slightly more complicated interactions. Like for instance, we have a scalar Gauss bonded interaction here. You can get some other mass rates. And the interesting thing about this mass rate is that it has a term that vaguely is recognizable. This is exactly the profile of a thermodynamically evaporating black hole. But obviously, you have this leading coefficient, which is a constant. And actually this also has remnants. If you solve it, you would find that it also has this cutoff mass, and it has the same behavior as we see here. Okay. Now the thing is that up until now we have seen that this effective field theoretic method is only giving you non-thermodynamic evaporation. So you might suspect this mathematics, because it's not giving you the standard Hawking picture, right? So to do that, we simply have to feed in the assumptions that went into the computation of Hawking radiation. And one of the key assumption was S wave dominance. And what that actually means is that the dominant modes that contribute to the mode expansion of your scalar field are S waves. So here you should have L and M to be 0. And that is what we have done here. So when you work with an S wave dominant mode expansion and repeat the same procedure of computing the effective action for the mass parameter and solving its equations of motion, you get you get back the thermodynamic profile. You get back the thermodynamic profile. So essentially, if you work with the path integral picture, or rather effective field theoretic methods, you get a wider class of accretion and evaporating configurations. You are not restricted to just, let's say, Bondi accretion, or you're not restricted to just Hawking radiation or thermodynamically mediated radiation evaporation. You get a much wider class of evaporation profiles, and that is the reason why we titled our paper non-thermodynamic black hole evaporation. And yeah, I think I would end my talk here. These are the references. So if you have any questions, you can certainly ask me. Yeah.
Okay, thank you for the nice talk. Any questions from the audience? Please unmute yourself and ask. Okay, I have one question. So,
Yeah.
other than the Vaidya metric, have you tried to explore any other metric, and does it also depend upon the kind of gravity theory you have? For example, if you have some non-local gravity or stuff like that.
No, we have not gone beyond the Vaidyametric because the problem which we are trying to study was that um, one another assumption in Hawking radiation is that the radiation is very feeble. So it is so feeble that the mass of the black hole does not change that much. So that is the reason why in most of these computations they simply work with a constant mass, and the quantum fields are coupled to some sort of an you can call it an eternal black hole, and you get Hawking radiation. But we just wanted to take that problem one step further. We wanted to make it a little bit more challenging.